because it's easy to get lost if you're just trying to read through the material. And at times I've studied ahead and didn't know what to do, so when the class comes around, I'd be prepared with questions on like, okay, this is where I got lost, where can I, what is the explanation on why that's happening?
Well, at CRC, I believe they do teach this class and along with most of the CISP classes online. Which is great for people who like to take classes online. But from what I was told, there's a lack of interaction between the professor and the students.
Yeah, I've taken a bunch of online courses from all sorts of different types. The only thing I haven't taken online is like a science course in physics.
Okay.
And I'd say that's the one thing. I feel like I learned the material all right, but I don't really feel like I know anybody after I get done with the class. And I think that has to do with most of the teachers that I've taken classes online from, they don't have any video recordings or anything like that. They don't have any recorded lectures, so you don't really get to know who they are.
I see. And there's also a lack of interaction between students and the professor, depending on how quickly they respond to forum posts and email.
Right. Most of the classes that I take online have required forum interaction between peers, so I actually get to know the other students fairly well. It doesn't require forum interaction from the instructor, so that oftentimes they don't really talk very much.
I see. Okay, that's interesting. But would you take this class online? I mean, it's actually pretty hard for me to teach online classes because I kind of like to go, go different places depending on the flow of the day.
I'd be okay with it.
You'd be okay with online?
Yeah. Although, I do also appreciate having the in-class.
The interaction?
Yeah.
I think with computer science classes, it is a little bit different from the other classes because with computer science classes, people who get to this class are mostly, INTP or close to INTP in terms of personalities. So they're all kind of, most people are kind of more introverted. As a result, they don't really interact a lot in class, in a whole lot of ways. But if you're taking psychology classes, it's a whole different thing. I know people who teach psychology classes online, and you look at their forums, in one day they have this much interaction, and most of it is not even required. The professor did not ask, okay, you have to post 5 or respond to 20. They just go like that, over the course of one day. And then you look at the computer science classes where it is required, this is your homework assignment. Read the post of somebody and respond to it. Fine. I just read your post. It's okay. So I guess it depends on the personality as well, of the people who make up the class. All right, so we are having a homework assignment. It's called recursive linear search. Okay, so this is your homework assignment for this week. So what you need to do is to rewrite the linear search algorithm in a recursive way so that it can be analyzed using the Master Theorem. Note that the Master Theorem only applies to algorithms that divide a big problem into smaller problems, but only in a certain way. We will get to the Master Theorem today. Okay, we set up everything on last Thursday, so that today we can actually talk about the Master Theorem. Your program needs to be written in C++. No, that's Monday. Okay, today is Wednesday. So that was Monday. Your program needs to be written in C++. The source code that you submit must have a file name of main.cpp, case sensitive. Do not zip or otherwise process the source file prior to submission, just the text file. Okay, so there's no need to zip or turn it into a tarball to turn it in. And these are the requirements/specifications of this assignment. The program itself must be self-contained and not rely on any other programs. The input is the standard input file. Okay, so if you're using C++, it's cin. If you're just using regular C, if you like scanf and that sort of thing, it's stdin. Okay, standard in. The first line of the input, which is a text file, indicates the number of entries as a base 10 non-negative integer. We'll call that n. The next n lines are base 10 signed integers. They can be containing 32 bits, guaranteed, that are not sorted. Okay, so I'm not going to give you integers that are sorted, they're unsorted. And the last line is a base 10 number that is the number that you're looking for. We'll call it k. The output is a standard is also going to use the standard output file. The output should be a single base 10 integer. Okay, so don't tell me yes, no, succeed, fail. Give me a single base 10 integer. This integer should be non-zero if and only if k is one of the n numbers in the input, and it should be a 0 if and only if k is not one of the n numbers in the input. So is that okay? Does everybody understand what the input and output should look like? Okay. If your code, in your code, do not sort. Okay, so do not sort the array first so you can use binary search. Your algorithm must work with an array that is not sorted, and it must be recursive. The function that implements the search algorithm should have the following prototype. So the return type has to be an integer, and the array is passed as the first argument. Now, if you want to be, like really careful about this whole thing, you can add const whenever it applies. Okay. In other words, in this particular case, you can say const in front of all 3 parameters, but that is not required. Okay, so you can just use this one if you want to. A is the array of integers as an argument. Length is the number of entries in the array, and the function returns non-zero if and only if k is found in A. So k is the last parameter of this particular function. So are there any questions about the homework assignment? Does anyone want me to make an upper limit of as to how many integers I can give you? Or does everybody know how to use new and you can deal with any size array? Yes? Okay, all right. So that's your homework assignment. If there are no questions about the assignment itself, then we'll move on to talk about the Master Theorem today, just so that you know, okay, so how do I need to tweak the search algorithm to fit into the format of the Master Theorem? Yep.
Are you planning on recording?
I believe it is recording right now. I'll double check.
Oh.
Yep, it is recording. I set up the timer a little bit earlier, so it goes off by itself. Okay, so I'll leave the homework assignment on screen as I go to Master Theorem. And there are 2 links here. One link goes to I think it's a Wikipedia page. This is a Wikipedia page, and this is just my page. Okay, so the Master Theorem, make sure there are only certain types of algorithms that can fit into the framework of the Master Theorem. In order to fit into the Master Theorem framework, the time requirement or the time complexity to solve a problem of size n has to fit into this particular format. So you have to be able to divide the problem into B parts. Okay, so that's why each subproblem only has a size of n divided by b. The A does not have to be the same as B. Okay, so A and B are can be potentially 2 different numbers. So A is a factor of that you have to multiply to n divided by b. And then on top of that, you have to add to it a function f of n. And f of n is basically how much time in a particular invocation do you have to spend without counting the recursive part that depends on the size of the problem n. Okay. So are there any questions about this particular format? No questions? Okay. So the rest of this, this particular paragraph here is really just a text representation of what I just said. Okay, you have a problem, original problem has a size of n. You divide it into, A is a number. Okay, you divide it into A, and then each subproblem has a size of n divided by b. So A and B do not have to be the same. Okay, in fact, most of the time A is less than B, but they can be the same in some cases. F of n is just a function that tells you, how much overhead you have per invocation of the subroutine. It can depend on n, but most of the time it is just a constant. It all depends on the algorithm itself. So we can look at binary search. Okay, so let's take a look at binary search. And in binary search, A is 1 because we only have one half of the problem to solve. Before we divide it into two halves, but only one half applies when you're doing the recursive call. And B is 2 because the subproblem is approximately one half of the size of the original problem. F of n is k, which is just a constant because it is a fixed number of steps that you have to perform per iteration or per invocation. Is that okay so far with binary search? With merge sort, if you turn it into a recursive call, then A equals B because you are dividing it into two problems, but you have to solve each problem individually. So you have B being 2 and A is 2 as well in that case. F of n in the case of merge sort is Kn because the merge step is proportional to the size of the problem. Because you end up with n items being merged, and each one has to merge individually, so you have to spend kn time to perform the merge part of merge sort. So are there any questions about how these two algorithms break down, but in a way that the Master Theorem can process it? Yes? No? Is that okay? Okay, so I want to go back to a previous slide, just as an example of something that does not fit into the Master Theorem. I'm not going to get out of this slide. I'll just go back to a previous one. That's an example. Okay, so this is factorial using recursion. Okay, but it doesn't fit into this scheme. Okay, because the subproblem. Because if n is the size of the problem, the subproblem has a size of n minus 1. It is not a ratio. Okay, it is not n divided by 2 or n divided by 3. It is not a fraction of n. It is n minus 1. So there's no way we can actually apply the Master Theorem on factorial because it doesn't fit into that particular scheme. Is that okay? So in order to use the Master Theorem, the big problem that is given to a particular invocation of the recursive subroutine has to be broken up into subproblems of about the same sizes. They all have to be like a certain fraction of the original problem. N minus 1 is not a fixed proportion, and as a result, the Master Theorem does not apply to this particular way of doing factorial. Any questions about this part? So now the question is, if you are doing linear search, or if you're working on a search algorithm that can work on an array that is not sorted, how can you make it recursive and yet make it so that you can use the Master Theorem to analyze the time complexity? So getting back to this slide here, which talks about the Master Theorem, or the first part at least. So your job is to look at the search algorithm that can search through an array that is not sorted, so that you are given a problem of size n, or you're given an array that has n elements, but each subproblem when you perform the recursive call is going to have a size of n divided by b. Now, is b going to be 2? I don't know. Is b going to be 3? I don't know. Okay, so you have to kind of decide how you want to structure your code, but you have to make sure that the subproblem is a fraction of the main problem. Is that okay?
It's unsorted.
It is unsorted, correct.
So
So one way you can look at this is to say, is to do it as a person, okay? So somebody gives me a stack of cards, okay, and each card has a number on it, okay? And your job is to say, and then that person will give you a number and say, and ask you, is this number a part of this pile of cards? Okay, that's your job, is to find out whether that is the case or not. And you know the pile is not sorted, and you're not allowed to sort it first. So how would you solve this problem when you or yourself is only allowed to see one of the cards? But you can tell somebody else, you divide the problem and give a portion of the stack or a portion of the pile of cards to somebody else and say, hey, I need you to help me. This is the number that I need to find in this pile. tell me your answer. And then you can give another person something similar. Okay, so the question is, how do you divide a big pile that you started off with into smaller piles, and each smaller pile must be about the same size, which is a fraction of the big pile that you're given with. Is that okay?
Yeah.
Okay. So you have 1 week to work on this. The code itself is not going to be taking too long. Okay, it is really a matter of, it's more of a thought exercise than it's an actual programming exercise. Because once you figure out how to divide a big problem, the actual code is actually not too bad. Okay? So I'll give you guys one more clue. Okay, so let's just say that with each invocation of the subroutine, you are only allowed to look at the top card. So what do you do with the rest? That becomes the question. Okay? Are there any questions about how you would proceed to do the homework assignment? No questions? Now it's due next Wednesday, which means if you're really stuck, you can ask questions on Monday or come to my office hour and ask questions. All right. So now that we know only certain types of problems or only certain types of algorithms, recursive algorithms, can be analyzed using the Master Theorem, let's take a look at, okay, but what about the actual time complexity in terms of big O notation when we already know what is A, what is B, and what is f of n? Okay. So as it turns out, it is summarized in here. Now, for those of you who really like to read a lot, you can go to the Wikipedia page and read this entire page. Okay, it is not required. Okay, the only reason why I have this one here is to summarize everything that is in the Wikipedia page, so that you don't have to dig through everything. All right, so this is a multi-branch conditional statement. So there's if, else if, and else if. So the first question you have to ask is, what is f of n? Okay, if f of n is big O of n to the power of something, this c, and this particular c here is less than log, using b as a base, of a, then the following applies. Okay, so let's double check and see if we have that, we meet this requirement using our binary search. Okay, so look at binary search and see if it fits this particular pattern. I can actually show both at the same time on the whiteboard. All right, so the key is, what is C? What is log B, using B as a base, of A? B in this case, when we look at binary search, B is what? B is 2, right? Because we are dividing the problem into halves. And what is A? It's spelled out over there. A is 1. So what is log, using 2 as a base, of 1? Now log of 1 doesn't really depend on which base we're dealing with. The log of 1 is always 0. So in this case, what about f of n in this case? In binary search, what is f of n? It's on the projector. F of n is k, which is a constant, right? So f of n as a constant is big O of what? Okay, so let's go back a little bit and figure out what is the big O notation, because this is something that we talked about only on Monday, so we haven't really have a whole lot of chance to kind of work out examples of the big O notation. Okay, so we know f of n is just k, which does not depend on n. Okay, it's just a constant. The big O notation, okay, so big O of g of n, okay, when I say f of n equals to this. Now in this case, I can actually make this big theta, okay, but we'll just say big O. What does that mean? When I say f of n for any function f of n equals to big O of g of n, what does that mean? Just in the grand scheme of things, not using mathematical symbols, g of n is a, when you plot it out, what is g of n? When you look at the picture, remember, right? You drew a picture here, right? So you have some kind of f of n here. So what would make g of n using the big O notation in this case?
G of n is going to be greater than or equal to, like if you multiply g of n by a constant, then it'll be greater than or equal to f of n. So
Right.
in that case, like
It's
one
f of
g
n.
of n could be like linear.
So you can find k1 and k2. Remember, there are two constants involved, right? So you can say k1 times g of n plus k2 is going to form an upper bound for f of n. That's the definition of the big O notation. Okay. So this axis is just n, and this axis is the result of the functions being applied to n. Is that okay?
Yeah.
All right. What about big omega of g of, let's pick h of n in this case. So I would still use f of n as the function that I'm estimating, but this time I say f of n equals to big O of h of n. What does that mean? Well, it means exactly the opposite. H of n can become a,
Do you mean omega instead of O there?
Oh, it's
Because-
big omega,
Okay,
yep.
I just got confused.
yep, you're right, it's big omega, omega. I have to spell out omega in this case because it's a text editor. I can't really enter the omega in.
Unicode?
I don't think mouse pad can deal with Unicode. No, I'll just use omega. So what does it mean when it's big omega of h of n? H of n is a
Lower bound.
lower bound. Okay, so now we have k1 times h of n plus k. Well, okay, let's pick k3 and k4 because I cannot use the same two constants. So basically, that's what it means to have a big O, which is just by using tweaking k1 and k2, it forms an upper bound. And this is what it means to have a lower bound by tweaking k3 and k4. H of n, the shape of h of n becomes the lower bound of the function that we're trying to estimate. Is that okay? All right. So knowing this, what if f of n is just k? In other words, we know what f of n is in the case of binary search. It's just k, which is constant. So what should I use as a big O notation? So I'm looking for something like this. Okay, f of n is k, and I'm looking for some g of n. Okay, g of n is what? So that when I multiply g of n with a constant k1 and potentially add a k2 to it, it is always going to be an upper bound of f of n, which is k, constant k. What do you think?
Would that also be a constant? Would it also be a constant?
Can be a constant, and what is the simplest constant you can find? Because you can tweak k1 and k2, right? So what is the simplest constant that I can use as g of n when I have all the k1 and k2 to choose from?
0 or 1, I would say.
0 or 1, exactly. So I would pick 1, okay, because it's non-zero, because when you have big O of 0, it's kind of tricky. So in this case, it can be 0, but I'll just use 1, okay? So when g of n is 1, I can quite easily find a k1 that is just k plus some minute distance. Then that will make the it will fit the requirement to become the big O. And I can also do the same thing for big omega in this case, because I can just find a k1 that is just slightly smaller than k, and that will fit that requirement. Is that okay? So the bottom line is when you have a constant as f of n, then the big O notation for that is just a constant. You can just say that g of n is just 1. Is that okay? All right. So now that we know that n to the power of c, now how do I make n to the power of c being 1? when n is the size of the problem, which can change. N to the power of what is 1?
0.
0, very good. So c is 0, and so is log 2 of a. So what do we get here? Is this requirement met? That 0 is less than 0? Nope. Okay, doesn't fit that requirement. So now we need to move on to the next one. Okay, so this is the next one. The next one is asking, can we use this to look at f of n? Now f of n we know is a constant. So can a constant be expressed in this way? And then we have some extra constraint here. The extra constraint is c equals to log b of a, which in this case is 0. So we have n to the power of 0 times log k of n. Do we have a log k of n as our theta? Okay, what is big theta, by the way? What makes a function usable as a big theta of f of n? It has to do with big O and big omega. So what makes something a big theta?
F of x is considered big theta of g of x if g of x if f of x is equal to big O of g of x and f of x is equal to big omega of g of x. Basically, the ratio of f of x over g of x is going to become a constant eventually.
That's one way to look at it, but by definition,
It's not
if
going to be
it's the
finite
same
here.
function, if you can make a g here as well, if g can be in both places, it can both be used as the upper bound and the lower bound. By tweaking k1, k2, k3, and k4, you can make a g to be served both as the upper bound and the lower bound. Then g can be used in the big theta notation. So in this particular case, you can say f of n equals to big theta of g of n. Because g of n is now a very good estimate of f of n, because it is forming both the upper bound as well as the lower bound.
Up to a constant though. It's all up to a constant though. So
Yeah,
like,
you're tweaking 4 constants basically. You're tweaking both k1, k2, k3, and k4, but you can make it fit. You can change the size, you can scale, you can also change the offset so that it can both be the upper bound and the lower bound. Is that okay? All right, so given that is the case, this requirement is not met because we don't have a log k of n component here. So now we have the last one. Okay, let's see if f of n fits in this particular format. F of n equals to big omega, and in big omega we have n to the power of c, and in this case c is greater than the log b of a, and a times f of n divided by b is less than or equal to k of f of n. Does it fit that particular requirement? Okay, well, let's check it one at a time. Okay, it looks kind of complicated. Does it fit the first requirement? F of n is big omega, n to the power of 0 in this case. Fits that requirement, right? What is f of n again for binary search? K, which is a constant, right? And as a constant, can we use 1 as g of n, and just by tweaking k1 and k2 and make 1, f of n being 1, g of n being 1, and make it a lower bound of the constant k? Sure we can, right? We can just make a k3 here, k minus 1 for instance, and k4 being 0. And g of n, remember, is 1. So k3 being k minus 1 means this curve is just always below the curve that we are targeting. So it does meet that requirement. But it's going to fail the second requirement because c is a 0 in this case. 0 is greater than the log b of a is false. because log b of a in this case is 0. 0 is greater than 0 is not true. So that does not, it doesn't work. Okay, is that okay so far? Let's go back to this one, and just double check whether this one works or not. So in this case, we have f of n, which is k in this case, is equals to big theta of n to the power of c, and c is still defined exactly the same way, which is log b of a. In this case, is 0. So the second term is really the interesting part. Is we are taking log k of n. In this case, it is log n to the power of k. And let me see, where's the k coming in? Yep, in binary search actually fits in this particular pattern. So we can find the k. So I think the k can be chosen. You have to find what k you're dealing with. So in this case, the k is 0. So when you look at log n to the power of 0, it is just 0. So f of n does fit this requirement. And as a result, t of n, or the time requirement or time complexity of solving a problem of size n, it has a complexity of big theta of n to the power of c, which is 0, times log k plus 1. In this case, k is 0, so it's just log of n. So it's n log n. No, I take it back, it's just log n, because n to the power of c is n to the power of 0, so we just end up with log n. It does fit this requirement. Because the k is something, k is a existential. There exists a k where you can say that f of n equals to big theta n to the power of c times log k n, which is basically log n to the power of k. Okay, so are we doing okay so far or not? Let's take a look at the second one. Let's look at merge sort, okay? So in the case of merge sort, we know that A equals to B, right? Because you are dividing a stream into two streams, okay? And the two streams are approximately the same size. So A equals to B because they are basically just 2. Or whatever number it is the same. And then f of n is k of n, k times n, because we have to re-merge all the elements from the streams after the split, and the time to do the merge is proportional to the number of things that we have to merge, and that's the overhead of each invocation of the algorithm. So as a result, we have we have a equals to b, f of n being kn. So let's try to look into this and see if we can work out how we can fit this into this particular format. Okay, so I'm going to use the document here. Okay. So we know a equals b. So when a equals b, what is log b of a? Log b of a. We know a and b are exactly the same. So what is the log 2 of 2?
1.
1. What is the log 10 of 10?
1.
1. Okay, very good. So we know c is just 1 because this is how c is defined. Okay. All right. So what about f of n? We know that f of n is some kind of constant times n, which basically just means that it is proportional to n. Can we make it fit into this particular format by changing only this k here? Okay. What is k times n? The k can be eliminated because the k can be absorbed by tweaking the k1 and k2. So this k here in f of n is not even important. How do we get n? Well, we have n to begin with, but can we say this is n times n to the power of c? Would that work? What is c again for merge sort? C is 1 because it's log b of b, because a and b are exactly the same. Okay, so now everything hinges onto the second part, which is basically asking, can we find a k so that k times, well, I shouldn't use the word k, let's change, okay, let's change this one from k to another constant. We'll call that q. Okay, q is a constant, just like k, but I want to use k in this, on this part. So we take the log of n, okay, and we say to the power of k here. Okay, so this is the constant that we're trying to find. Can that work? Or make it at least proportional to. Now remember, q is no longer useful because it's just a constant. So we can take this out when we are looking at the big O notation, because this is basically big theta. So when we want to change it from an actual equation or an actual formula into the theta notation, the constant here is no longer useful, so we can eliminate it. And after we eliminate the q, we only have n left. N is n to the power of c because c is just 1. What about this part here? I want this entire thing to boil down to just 1. How do we boil that thing down to 1? We make k equal to 0. Very good. Okay, so k is made into 0. So it does fall into this particular format. So once we know that this condition is satisfied, then we can try to analyze the time complexity, which is this part here. So when we look at the time complexity, T of n is big theta of n to the power of c, but we know c is just 1, times log k log n, the whole thing to the power of k plus 1. What k did we pick earlier again? K equals to 0. So now that k is, we need k plus 1 over here, so we have it to the power of 1. And what is the easier way to spell this out? Big theta of, what is the easier way to spell out n to the power of 1? N, very good. And what is the easier way to spell out log n to the power of 1? Log n, yep. So the time complexity of merge sort is big theta log n log n. So once you know the time complexity of merge sort is n log n, now the question is, what is the worst case of the merge sort algorithm? N log n. What is the best case? N log n, because it is both the upper limit and also the lower limit. Are we doing okay so far with this? Okay, all right. What about linear search, your homework assignment? What is the time complexity of linear search? Non-recursive, just the usual way of doing linear search. What is the time complexity of linear search? So to take a look at that, we'll just take a look at a very typical implementation of linear search, non-recursive. So we have search, A is the array, n is the number of entries in the array, and k is what we're looking for. And that's fairly easy to do. It's just a matter of how fancy do we want to make this. Okay, so we can say it doesn't even need that. I just need an I here. So we can say for I equals to 0, we start at the very beginning of the array. I is less than n, which means I is still a valid index into the array, plus I. Okay, we want to add 1 to I. And in here, we don't even need that, because we can just say that as long as I is less than n and a bracket I does not equal to k, we stay in the loop. Let me change the size of the window first. And we don't need anything in the loop. And to return whether k is an element in the array or not, what should we return? If you took CISP 300 from me, you should know the answer because we did the same thing in that class. Okay, so let's take a look at this algorithm. What is it really saying? It's saying that I equals to 0 to begin with, which means we're starting from the beginning of the array, so there's no mystery in this part. The condition to stay in the loop, okay, I will just add some additional parentheses to make it extra clear, okay? To stay in the loop, I need I to be less than n, and on top of that, I also need a bracket I not to equal to k. Does that make sense to you? We stay in the loop as long as, 1, the index is still valid in the array, which means we have not seen everything in the array yet. And the one that I'm looking at right now, which is a bracket I, does not equal to what I'm looking for. So as long as there's more things that I can look in the array, and we haven't found what we're looking for, keep going. So it's going to exit as soon as what? As soon as I is greater than or equal to n, which means we have searched through the entire array, I is no longer a valid index, it's time to get out. Or I is still valid, but this condition is false. What does it mean when this condition is false? A bracket I equals k. Why should I exit?
Because you found it.
Because I found it, exactly. Okay, very good. So when you look at this algorithm, what should we return so that the return value is non-zero if and only if k is found?
A of I equals k.
Well, that can be dangerous, okay? Okay, so I'll talk about this one first, okay? So apparently it does work, okay? So if a bracket I does equal to k, that is the answer, okay? It seems to be the most intuitive answer, but we have a problem. What if we could not find it? Then I becomes
Out of bounds.
it becomes n, right? What is a bracket n? A bracket n is not in this array. Now, for the most part, because you're not changing a bracket I, so for the most part, it's not going to do any harm. But it can potentially give you the wrong answer because there's an off chance that a bracket I, which is not a part of the array that you're supposed to search, turns out to have the same bit pattern as k. Now, the chances is really low, but it can happen. So this may not be the best way to do it. Okay, what is the other way to do this? Can we rely on just I, the relationship between I and n, to determine whether we found it or not? Because if I exit, if I get out of the loop because a bracket I does equal to k, what has to be the relationship between I and n?
Is less than n.
I has to be less than n, exactly. So this would also give us the proper answer. Okay, because if I is less than n when we are out of the loop, then the only reason why we can get out of the loop is because a bracket I does equal to k, which means we found it. Okay, if a bracket I equals k, does not equal to k remains true all the time until we get out of the loop, then I has to be greater than or equal to n because that will be the only reason why we are getting out of the loop. So this is the proper way to kind of indicate whether we found it or not. Okay. Now we look at this algorithm and say, what is the time complexity of this algorithm? And let's just say, we take the worst case scenario in this case. In other words, we're looking for a k that does not actually exist in the array A. How much time does it take to do something like this?
Go through it n times.
Yep, you have to go through it n times, which means the complexity is not 1, because 1 means constant. It's not definitely not constant. It is proportional to n, exactly. So T of n in this case is big O of just n, because it's proportional to the number of items in the array. Now, by making this recursive, you really should not be changing the order of magnitude. Okay, so that gives you some clue as to how to construct your algorithm. Why does it give you some clue of how to construct the algorithm? Well, you look at these cases here, okay? And you ask yourself, which one can be an n? You look at this thing here and say, can this be n? The answer is yes, it can be n, but in order to make this n, log b of a has to be a 1. Okay? So if log b of a has to be a 1, and also, this also is a 1 over here, so you're looking for the case where 1 is less than log b of a, but at the same time you also want log b of a to be a 1. That doesn't work. Okay? So you kind of know that it won't fit into this particular format, which automatically means that this relationship does not hold. Okay? Well, let's take a look at the second one. You take a look at the second one because you already know this whole thing should boil down to just n. Okay? So now the question is, how can I make this whole thing boil down to just n? So n to the power of c times log n, the whole thing to the power of k plus 1. How can we make this into just n? What if we make, we also have the definition of c equals to log b of a. We know then, well, okay, so let's say this is 1, c is 1. If c is 1, then log b of a also has to be 1, which means a and b, they must be the same. Is that okay? So that locks down the relationship between a and b. We also want the second component, which is log n, the whole thing to the power of k plus 1 to be just 1. Can we pick a k to make that happen? Well, no one says k cannot be negative, right? So if you pick k to be negative 1, that can happen. You can turn log n to the power of k plus 1 equal to 1 because you choose k to be negative 1. Negative 1 plus 1 is 0, so everything to the power of 0 is just 1. So the second one does seem to be able to do it. Is that okay? But in order to make that happen, you need a and b to be the same. When a and b are the same, c is 1. You also have to take a k that is negative 1, but that's just something to make this equation work. Is that helping a little bit? Just by telling you that a and b must be the same? So when you look at a and b, I know this slide doesn't really show you how a and b relate to the algorithm itself, but when you go back to this slide here, or when you go back to the earlier part of this slide, that's where a, b are located when it comes to the analysis of the time complexity of the algorithm. If you just look at this portion here, t in parentheses n divided by b, that's the time for each recursive call. Okay? N divided by b is the size of each sub-problem that you are trying to solve using the recursion call, and a is the number of times you have to perform the recursive call. So in this case, the number of sub-problems is a, but that has to be the same as b here. Is that helping a little bit in terms of helping you to kind of figure out the structure of your recursive subroutine? Sort of? We also know what is f of n, don't we? Okay, so let's take a look at f of n in this particular relationship here. Okay, so in order to make this work, we also need to make sure that f of n fits in this kind of weird format. And c is 1 in this case. That can be a little bit tricky. That makes me wonder whether the first one is supposed to be a less than or less than or equal to. No, the first one actually does apply. Okay, I take it back. It's the first one that does apply to your recursive algorithm. Log b of a still needs to be 1, okay? So I'm already giving you a clue that a and b should be the same. What can c be when it is less than log b of a, which is 1? What is less than 1?
0.
Okay, first of all, can it be negative? Can it be a negative number? Well, it can be, but in this case it's not. Because if it's a negative number, it means it's proportional to 1 divided by n to the power of something, which doesn't really make sense when it comes to timing analysis for algorithms. So the only thing that can be less than 1 is a 0. Is that okay? So I'm already telling you in this case that we have f of n is a constant. That makes c a 0. 0 is less than log b of a, because a and b are exactly the same, so log b of a is actually just 1. And as a result, the time complexity of the algorithm is n to the power of log b of a, which is n to the power of c, which is n to the power of 1, which is n. So your recursive implementation of the binaries, not binary search, but linear search, is going to fit into this particular format. Okay. So key summary to help you with your homework is you know A and B are the same, which means C equals to 1. Oops, C equals to 0 in this case because C is less than 1, which also makes f of n a particular constant, just a k of some kind. Okay? Is that okay so far? How many people kind of have a pretty good idea of how to proceed with the homework assignment? Okay. No, not really? Okay. So let me see if I can find some props here. Well, maybe I can just draw something on the board. So you are given a huge pile of cards of some numbers, okay? And you are asked to say, okay, is K in this pile? Okay? But the only thing you can do is to look at the top part of the stack, or the top part of the entire pile. So you look at the top one here, because that's the only one part that is exposed to you, and you go like, that's not K. So now the question is, how do you divide this problem into something like this problem and give it to some people to solve that problem? And each person would take care of some portion, some proportion of this problem. That's the question. Okay? So cut the rest in half, right? Okay, because you took care of the top card already, but you can look at the remaining portion and say, well, let's just cut it in approximately half. It's not always possible to cut it in half, but it will be pretty close. So then what do? You pass one half to the next person and say, okay, here it is. Tell me whether K is in this pile or not. Okay, and then you pass on this pile to a separate person and say, do the same thing. Look at the top one and tell me, tell me whether K is in this pile or not. Yep, that's the way to do it. So the person who took this half, what is that person going to do? Look at the first one. Okay, look at this top card and go like, well, is that K? Nope. What would that person do? Split the rest of it in half and give it to 2 more people. When do we stop?
N equals 1.
Well, when the top card is the card that you're looking for, right? So when the first element of the array is in fact K, then you're done. What if K is not in the entire array? So that would never be true. So when do we stop?
When the last person gets 1 card.
When the last person gets 1 card, you can stop, because when that person who only has 1 single card and say, hey, the only card you gave me is not K, then the answer is definitely a no, right? Then you're done. And that person will return the answer back to the previous person. That previous person will integrate it into that person's own answer and then go all the way back. Is that okay? So it's a kind of strange way of doing quote unquote linear search, but it is linear in a way.
eventually go through.
Yep, eventually you'll go through every single card. It's kind of like binary. It's kind of like binary search, except you're not looking at the middle part. You're looking at the top part. But the way you chop the problem into halves is very similar. Is that okay? I mean, does that help you guys kind of figure out the algorithm? Okay. Because I don't want to give the pseudocode. That would be like giving way too much. But telling you this much is good. All right.
You already have that.
Hmm?
Yeah, you already have the base case and the main.
Right. The base case is easy. Is fairly easy because you have to terminate when you have no cards. You have to terminate because then you have to say no. If you only have one card, then you're responsible to look at that single one card that you're given with, and that is also a base case because you can say, hey, this is or is not what we're looking for, and that's your definite answer. There's no subproblem to divide it into. Okay. What if you're given two cards? What do? How do you divide it into subcases? Okay. Over here. So you are the one given two cards. Okay, 1, 2. You're only allowed to look at the top one. So you look at the top one and say, oh, that's not K. What are you going to do? Well, then you have two subproblems. The first subproblem has one single card. The second subproblem has no cards. That's okay, because you can make your recursive function handle both of these cases. Because when you can make your function so that when you're given no cards or when length equals to 0, you just automatically say no. Does it make sense? I give you an empty bag. Remember last time I said, I give you an empty bag and then ask, oh, is my phone in that bag? The answer is no. The bag is empty. My phone cannot be in an empty bag. Right? So when length is 0, which is this case here, you automatically answer without any comparison of any element in the array. You just automatically answer no. You're giving me an array of no elements. So obviously the value that you're searching for cannot possibly be in that particular array. So you can still apply it when you try to handle this particular case. Okay. Any other questions? No other questions? All right. Okay. So this is pretty much the entire thing about recursive subroutines and the Master Theorem. So this is really the key part of the Master Theorem. What I need to improve is over here, I have to say there exists a K so that this requirement is met. Okay, so I did not say that here. Okay, any questions regarding recursive subroutines or recursive algorithms or the homework or the Master Theorem? Yep.
So the goal of the homework is to turn that function into recursion.
Well, the way I drew it on the whiteboard is kind of recursive already because it splits a big problem into subproblems. So your homework is really just to code the logic of the logic, code the logic of the algorithm. Yep.
So when you say like a standard input file, you did it on the other homework as well, but we can name it whatever we want, right?
It means a standard input file, which means you can redirect input into the file.
Okay.
So if you're using C++, it is cin. If you're using regular C, it is just standard in or stdin.
Okay.
Yep.
Will you be grading the previous coding homework that we turned in so that
Oh yeah.
before we do this one so that we can make sure that if we did any correctly?
Oh, okay, I see. Sure. Yeah, we can do that. But I can also give you guys some clue here too. So
You graded with like a script, you said, right?
Hmm?
You graded with your own script.
Yeah, it is going to be graded with a script, but in this case, the script is really just, well, I can use the script to grade the entire thing, but I'm going to go through, just eyeball the whole thing too, just to make sure that.
Look at the code and everything?
Oh, I will read the code,
Oh, okay.
because in this case, it is easy to do it with just the regular non-recursive implementation, and even in the recursive implementation, they can use a way that cannot be analyzed using the Master Theorem. So I will be looking through the whole thing myself as well.
And the other one also, you also read that one?
The other one may or may not be the case because the other one, I think there's only one way to really implement it. Okay, but I do want to show you what it means when I say standard in, standard out. Okay, so I'll give you an example of using standard in and standard out. Okay, okay, I'll just do a summation example. Okay, so in this program, I am going to sum up all the numbers that are presented to me, and we'll just make the assumption that the first number indicates how many numbers, and then it will always be followed by that many numbers after that. Okay, so we'll just call it sum.cpp. And I will do it in, syntax highlighting is not useful in this case. So we say syntax off. Okay. And it's the IO stream in C++ when you need to use cin. Okay. And main. So the first number that I need to read in is just n, which is the number of entries that I need to add up. I need a some variable here, initialized to 0. And then on top of that, I need an x, so that when I read each number, I can add it to sum. So now I can say cin to n, and then while n, do the following. And I can say cin to x here. And I think I forgot to do the use namespace thing. Now, if you don't do the namespace thing, you can always just add it over here. Std, just add std : in front of everything, which is kind of cumbersome, but it's one way to do it. And then we say sum plus equal to x. And then the output is just going to be the summation. So if you just say std : out, cout. And we're outputting the sum, and we also want the end of line, so we have std : EOLN, I think. Is it EOLN for end of line?
It's NL.
NL? E, huh?
ENDL.
ENDL.
Yeah.
ENDL. Turn 0. And that's the so you program to basically read n numbers and just return the summation of those numbers. Now, in your case, it's going to be a little bit more complex because you have to store everything into an array in order to search in the array later on. But I'm just showing you how to use cin and cout in this particular example. Okay, so got to make sure it compiles, right? So we say G++, and when you use G++, I recommend people to turn on all the all the options. Wall stands for warn all, which means, okay, tell me everything that can possibly be a problem, okay? Pedantic is not usually required. It basically means that you only want to use the features in GCC or G++ that's also in ANSI standard, okay? So that's not usually required. -C gives you a object file, which is not something that's always needed. Okay, so everything is good, but in this case, I have a sum.o, which is an object file. I need to link it to the actual file. There we go. So now I can now test it. So the first thing I need to do, I can test it with just the interaction using the command line. So when I run the program, because it's reading from standard in, it's waiting for me to type something. Because unless you use redirection, standard in is corresponding to the console, which is the place where you interact with the command line interface. So I can say, okay, we're going to deal with 5 numbers and add up these 5 numbers. Okay, 99, 98, 97, 96, 95, and oh, I forgot one thing. This is also a good time to talk about debugging. How many people are using the command line to do the programming as opposed to, okay. So if you're using the command line to do the debugging, you might want to also add one more thing to it, which is -G. It turns on the debugger, okay? It turns on the debugger symbols in the object file. And when you link, you can also link with debug information. Okay, so now with debug information, I can use GDB to debug this particular program. I know what's wrong with it already, okay? I just want to kind of show you guys how to use the debugger. So you use GDB, and you run the program in GDB. Okay, and you say, okay, give it 5 numbers. Let's give it 2. Okay, just say that we want to add up 2 numbers. And we say 1, 1, 1, 1. Hey, it's not stopping. How come it's not stopping? So now the question is, in GDB, how do you say, hey, stop everything, pause. Control C, okay? Control C will pause the execution of a program, and it will even tell you where you are, okay? We are currently in some kind of read operation, which makes sense because it's waiting for me to type something. But who's calling this, okay? How do I get back to the other parts? Do you guys know how to show where you are or how you got here in the first place? Starts with a B. Not exactly. Backtrace, BT. Okay, so when you say BT, it gives you some a whole bunch of mumbo jumbo. Okay, at some point it's not going to be mumbo jumbo. So it gives you this whole thing. But when you look at this, these are the call frames. Okay, number 0 means this is the current call frame. This is what the Control C is really interrupting. This is the next one. This is the higher up. In other words, we start everything from main. Main is calling the reading, the read operator for an IO stream. That in return is calling sentry. Sentry is calling stdio sync file buff and so on and so forth. But I know where I was in the program. Okay, the call to read something is on line 12 of sum. Okay, so now I have a general idea of what is in the infinite loop. Okay, what is involved in the infinite loop. So once you know where it is in the infinite loop, you're on line 12 of sum, you can use the list program to say, okay, show me line 12 or everything around line 12, and you can see that, hey, this is around line 12. The mistake should be fairly obvious at this point, but let's just say it is not. Okay. Because the only way this loop should exit is when n gets down to 0. When n is 0, then it is considered false, and we should get out of the loop. So I'm just asking, okay, so what is n? N should be 0 by this time, but it's not. Okay, it's pretty clear that n is still the same as before, but I need to confirm that. How do you confirm that? In GDB. So in GDB, you can say frame, okay? So when you say frame, you have to refer to one of these numbers here. So the only frame that makes sense to me is the frame that is in the program that I'm writing, which is frame number 7. So you say frame 7, and that will basically put the context of the debugger back into frame 7, where x, n, and sum are all defined, okay? So at this point, because I'm in the right frame, I can now say, okay, tell me what is the current sum? 4, that seems to make sense because I have entered 4 ones. What is n? Did I enter 1 incorrectly? No, I entered n to be 2, so that's definitely, oh, wait a second here. I've entered 4 numbers already. N should be 0 a long time ago, and it's not, right? So at this point, I can go back here and go like, how come n is not being changed? Well, why is n not being changed?
Because you never change it.
Because there's no code to change it. Exactly. Yep.
Is that an S2 equals to 2?
Huh? Where?
Dollar sign.
That's a dollar.
Yes, a dollar sign, which basically let you refer to $2, then it will give you the value of 2. When you refer to $1, it gives you a value of 4. So you can refer to the value of something that you have evaluated earlier without having to copy and paste it. Not really particularly useful in this case. So this program is not working. Fine, we will go back and change the program. Because I forgot to change, okay, sin off. Because I forgot to decrement n after we read the number. So you can do n minus equal 1, minus n minus minus, they all do the same thing. So this time it should be right. Okay. So we'll say g++ dash g dash 1 all dash pedantic dash o. I'm just going to give me my executable right away. Like so. Okay. So now when I run the program again, this time it should run correctly. Okay. Add 2 numbers. 45 and 67. Gives me a sum of 112, so that's good. Question?
So on the previous homework, I didn't really use C in and C out exactly like that. Will I still be able to be graded? Should I change that now?
Don't change it now, because if you change it now, the Moodle will forget what you turned in earlier, as well as the time that you turned that in.
Like my problem was, or my solution was correct, but I just gave it like a named input file.
Okay.
I didn't know to do that. I've actually never used C++ before this 5.
But the prerequisite is 430.
I took this equivalent at Sac State and it's all in Java.
Okay, gotcha. So you had to learn how to use C++ because your only exposure was Java.
Correct.
Aye. Huh? Sorry?
State this job.
Well, they only use C in one class. I think the systems programming class is the only class where they use C, so they have to spend half the semester to talk about C so that people can actually write programs in C in the second half of the semester. Okay. Yep. Any other questions? I think the standard input file also exists in Java, except it may not be the same mechanism. The mechanism to read from standard input file is not the same. Okay, but once you have the standard input file, you can test your program using a file. So I can now say, test.txt, you can name it any way you want. But in the file, I'm going to say, okay, there are 6 numbers, and these 6 numbers are, 5 and then 6, like this one. So now I can test the program by redirection. I can now run the program by redirecting the file as standard input. So the less than simple is redirecting whatever is after that as standard input file. So instead of having to type all that stuff that is actually in this file, I can now just run this program with the redirection. When I press the enter key, it will give me the answer because standard output file is not redirected. So it just gives me the answer. And this is a very handy way to test a program. Okay, especially in your case, because in your case you probably will have a certain number of things to search from, and if you want to have a consistent test every single time, this is the best way to do it. And this can also be done in GDB. So for those of you who really want to use a debugger, you can do it in GDB as well. You can actually do a R, which is run, and then less than, which is the redirect symbol, test.txt, it will do the same thing. If you set any breakpoints in the program, if you say breakpoint on line 12 and run the program with a test.txt redirection, it will still stop. Okay, and at this point you can look at the various variables in the program. You can say print what is x, what is n, what is sum. Okay, x is kind of a strange value. Why?
Garbage hasn't received anything yet.
Yep, this is our first iteration. Okay, nothing is in x yet. X is uninitialized, so it can be anything. Okay. All right, there we go. Any other questions regarding the homework assignment? So I'm hoping that this, if I don't end up grading the homework assignment, the previous one, fast enough, I hope this will kind of help you guys kind of know how to structure a program. Is anyone going to use scanf and printf? No. No. Okay, so then I don't have to explain that. All right. Okay, very good. So now that we are done with the Master Theorem, we are moving on again. This time we are moving on to graphs because we kind of talked about, well, let's go back to probability because it's here. Okay, when we talk about this probability, it is conditional probability and we're going to talk about Bayes' theorem. This is actually my notes as well. Okay. So let me see how much time do we have? We have about 8 minutes, so it's a good way to get it started. And on the next Monday, we can answer questions about the homework assignment and also continue with conditional probability. So, but we'll get a first taste of conditional probability today. And we'll take a look at the definition first. Okay, so we take a look at the definition. And do you guys still remember what is omega? When we talk about probability, what is omega? Omega is a set of
Possible outcomes.
all possible outcomes. Very good. Okay, so now we want to define a certain predicate called A. Okay, so A is a predicate, and AX, X being an element of omega, is basically saying, are we interested in A? Are we interested in X in this case? B is another predicate. So as a predicate, it can either be true or false. Okay, so A of X can be just asking, is it a head? Okay, is a particular coin toss a head? And B can be asking, is it a tail? So in this case, we also use the simplification. So instead of using A as a predicate, we use A to represent the set of all the elements such that A of X is true, and that has to be a subset, and possibly a proper subset, but it can also be just omega itself. So A is less than, a subset of omega. So A is representing a set of outcomes that we might be interested in out of all possible outcomes. Is that okay? So A can be the case like omega can be all car accidents, and A can be all car accidents where the driver is less than 30 years old. Okay, that can be one way to define A. And the definition of B is about the same. So in this case, B can be look at all car accidents. Okay, so omega will still be all car accidents, and then B can define and say, give me all the accidents where the driver is also drunk at the time. Okay, so then we have A, which is a particular set of all the outcomes, all the car accidents, and B is also a subset of all the possible outcomes. The ratio P of A is really just the ratio of the cardinality of A, which is in this case, the number of cases where the driver of a car involved in a car accident is less than 30, and omega is the cardinality of omega is the number of all accidents that I'm considering. So P of A is really just the probability of what are the chances that in the car accident that the driver involved in the car accident or causing the accident is less than 30 years old. Is that okay? And the same thing with P of B. Okay, so PB is the chances of the driver involved or causing an accident is drunk at the time. Is that okay? Now we want to look at conditional probability. This part is the most important part. P and an A with a bar B, okay, is the conditional probability. The conditional probability of A given B is the probability of A intersecting with B over the probability of B itself. In other words, we are counting the number of cases where, tell me all the number of cases where the driver that is causing the accident is younger than 30 and drunk at the same time. Okay, that's what the numerator is. The denominator is still the number of people, or the number of cases where the driver responsible for the accident is drunk. So now I'm looking at the conditional probability of being less than 30 and drunk at the same time over just being drunk. Is that okay? Or not? Why is that important? So let's say you are running an insurance company. Okay? Why is this important?
So they can charge you more if you're gone.
But how do you know who to charge more?
You analyze all the accidents.
Okay, so there are several ratios that we have to look at, right? So we have to look at the ratio of just PB, okay? PB is bar B over bar omega, okay? Which is, overall speaking, looking at all the accidents. how many times, or what is the proportion, or what is the probability that a drunk driver is causing the accident. Okay? And then we look at the conditional probability, P, and in this case A bar B. And we are asking, okay, let's look at the A intersecting with B, which means less than 30 and drunk, divided by just drunk. Okay? What is the significance of A bar B? Okay, just think of the extreme cases. Think of extreme cases. What if A bar B is 0? What is that telling you?
No one under 30.
No one under 30 is going to be drunk while involved, causing an accident. Okay? If that is the case, how would you change the policy as an insurance company?
Lower risk.
It'll be lower risk. At least you know that if somebody is less than 30, that person is unlikely to be causing an accident because of being drunk. Okay? What if it is 1? What does it mean when it's 1? When it's 1, it means A intersecting with B is the same thing as B, which means A equals B, which means
Every drunk accident.
yes. So in that case, okay, if the applicant to get insured is less than 30, what would you do as a policy for the insurance company?
Higher risk.
Probably high risk. Okay, so that's how
profiling.
you want to look at these numbers. Okay, is that okay so far? Okay. So that's why conditional probability is important, because you're not looking at the big picture. You're basically saying, okay, within a subgroup of the entire group, okay, we're looking at the subgroup and see how it relates to the entire group. So here's Bayes' theorem. Bayes' theorem is just saying, okay, it's just symbolic manipulation. It is just saying that P, B bar A, the conditional B over condition A, it can be expressed as this. And the proof is this, okay? This is a step-by-step proof of Bayes' theorem. Okay, the first part here, the first line, is just the definition of conditional probability that you have seen a little bit earlier. Okay, so that's no mystery. This one, okay, you take this one over here. Why is this equal to this? Well, that's because intersection is commutative. A intersecting with B is the same thing as B intersecting with A. You take this one over here, and then you look at this particular thing. Well, that's because we just multiply the whole thing by PB and then divide the whole thing by PB. PB divided by PB is always 1, so we know, hey, this is okay. And then the last step here is to take this chunk over here by rearranging, this whole thing into A bar B by definition of P of A bar B. Then we have PB over here and a PA over here. So now we went from the beginning all the way to the end, proving the theorem. So that's just Bayes' theorem, which you can do by the definition of conditional probability. We don't have enough time here, but for those of you who want to read this, you can read this part here. Okay, cases of how you can make use of and also abuse conditional probabilities. So in this case, it has to do with the use of string copy and the program being hackable, because those two have some kind of correlation. So just kind of read through this part here, and we'll continue this discussion on next Monday. Yes.
Can you upload the video?
I will upload the video. Yeah. It is recorded today. I made sure.
Oh, it's really recorded today.
Yes.
Okay.
Yep.